Hello everyone and welcome back to the channel. In this video we're going to talk about exponential growth and decay. So exponential growth occurs when a quantity increases by the same factor over equal intervals of time. Okay, so increasing by the same factor. So we have an equation for exponential growth, and our exponential decay equation is going to look almost exactly like this, but we'll see that in just a minute. For exponential growth, we have y equals a times the quantity of 1 plus r, and that quantity 1 plus r is raised to the exponent of t. So we can see what all these variables represent. Y equals, so y is our final amount, a is our initial amount, r is our rate of growth, and it's important to note that is inserted as a decimal. So if they tell you our rate of growth is 8%, we're going to put that in as 0.08. And then t represents our time, and that's in years, okay? 1 plus r, that's our growth factor. So if we have a growth of 8%, our growth factor would be 1.08. Okay, so let's look at an example with exponential growth. It says the inaugural attendance of an annual jazz festival is 90,000. The attendance y increases by 7% each year. We want to write an exponential growth function that represents the attendance after t years, and then we want to see how many people will attend the festival in the 8th year, and we'll round that to the nearest 1,000. Okay. All right. So we look back at our equation, and we can write that down. We have y equals. We'll change up our color here. Let's go like a navy blue. Okay. Y equals a times 1 plus r, and we're going to raise that to the t power. Okay. So y is basically what we're going to be solving for. A is our initial amount, so we have y equals 90,000. 1 plus r is our rate of growth, which is 7%, so we're going to insert that as a decimal, 0.07, and we're going to raise that to the power of t. So now we can simplify that growth factor to get a final equation of y equals 90,000 times 1.07 raised to the power of t. Okay? All right, so now we're going to use that equation for part B. Part B says how many people will attend the festival in the 8th year, and we're going to round to the nearest 1,000. So all we're going to do is take our equation, y equals 90,000 times 1.07, and now we're going to raise it to a power of 8. Okay, so now we can take our calculator, and we can type in 1.07, raise it to the 8th power, and we get 1.718, so on and so forth. So now I'm just going to use my calculator now, leave that long decimal in there. I'm going to multiply that right by 90,000. So I'm going to hit times 90,000, and we get y equals, and we have 154,636.76. Okay, now the question said round to the nearest 1,000. Okay, so we have 154 and 636, right? So we're going to say 155,000 people. Okay. All right. Now let's take a look at exponential decay. So exponential decay occurs when a quantity decreases by the same factor. So now we have decreasing by the same factor over equal intervals of time. So if you look at our equation, it looks almost exactly the same, except for now we have subtraction inside of our decay factor. So now it's called a decay factor and not a growth factor. So one thing that we can hopefully take away is if our factor inside is more than 1, then it's an exponential growth equation. And if it's less than 1, then it's an exponential decay equation. Okay. All right, so let's determine whether these tables represent an exponential growth function, an exponential decay function, or possibly neither. So let's look at our first table. So our x values, right, we are just increasing by 1, right? Plus 1, plus 1, plus 1. And remember with exponential, we want to check to make sure, are we multiplying by a constant factor, okay? So when I look at this, 360 to 180, 180 to 90, 90 to 45, it looks like we're dividing by 2, right? We are, but we want to talk about that in terms of multiplication. So we're going to say multiplying by 1/2, okay? So multiplying by 1/2, that number is less than 1. Obviously, we can see that as our x values increase, our y values are decreasing. So this is going to be an example of exponential decay. All right, now let's look at the second example. X values are still increasing by 1. So that's a constant increase there. And now we look at our y values. 4 times 5 is 20, 20 times 5 is 100, and 100 times 5 is 500. So this would be an example of exponential growth because our y values are increasing exponentially. And the last example, x value is still increasing by 1. But now let's look at our y value. So let's say, okay, 3 times what is 9? Times 3, right? Well, is 9 times 3 15? No, it's not. So maybe we're not multiplying here. Maybe we are adding. So plus 6, and plus 6. Okay, so this would actually be an example of a linear function. So it is not exponential, therefore it's not growth or decay. All right, let's look at another example. A couple more. It says, does each function represent exponential growth or decay? And then what is the percent rate of change? So here, all we're looking at is our growth factor, or it might be a decay factor, right? We talked about this a minute ago. We said if that value inside the parentheses is greater than 1, then it would be growth. If it is less than 1, then it's going to be decay. Okay, why is that? Because if we have a value that's more than 1, that means we had to have added something to 1. And when we have the addition in there, that's our growth function. So here we have 1.09. So what did we add to 1? This was 1 plus 0.09. So right here, this is our rate of change, our percent rate of change, but it's as a decimal. So when we write it as a percent, we want to write that as an actual percentage. Okay? So this is growth, and it is 9% growth. And for example B, we saw this was decay because what did we subtract from 1? 1 minus what gave us 0.96, right? Well, that would be 0.04, right? So we subtracted 0.04, we get 0.96. So this is a 4% decay. Okay. All right, last two examples we're going to look at. We're going to rewrite these functions and tell whether they are growth or decay. So if we notice here, look at our exponents, right? We have t divided by 6, and then we have t minus 2. So what this reminds us of is our properties of exponents. So if you want to review that, check out the video in the top right-hand corner. So we start off with example A, and we have y equals 57 times 0.98 raised to the t divided by 6 power, okay? So t over 6, remember when we had rational exponents? What we want to do with that is make that become 1 over 6. Okay, so I'm going to say y equals 57 times 0.98, and I'm going to change this to 1 over 6. And then what do I multiply 1 over 6 for my exponent to be t over 6? Well, that would just be t, right? So now that would be an example of power-power product. So 1 over 6 times t would get me to t over 6. So essentially what we did is we undid power-power product, so that now we can evaluate this 0.98 to the 1/6 power. So now we can do that in our calculator. So we can say 57, and then in parentheses, now in our calculator, we're going to say 0.98, and we're going to raise that to the 1/6 power. Okay, and that gives me 0.9966, so I'm just going to say 0.99. Okay, so now we can see, okay, that factor inside the parentheses is less than 1, so this must have been a decay factor. Okay. All right, and the last example, our exponent here is subtraction. Okay, so we think back to our properties of exponents, and one of the examples that I talked about was, or one of the properties was MADS, right? And that told me if I have two expressions that have the same base and we are multiplying them together, we can add their exponents. If we are dividing with the same base, we can subtract their exponents. So we see here we have subtraction. So we could rewrite this as 1.3 to the t divided by 1.3 to the second power. Okay, the reason we do that, if we looked and we saw this right here, what would we say? We say, okay, we have the same base, so we can keep the base and we can just subtract the exponents. Well, that's the same thing we see at the start, right? So basically, once again, we just undid that exponent rule, okay? So now we start here, and what we're wanting is for it to look like this over here, right? So we need that denominator not to be there. Well, if we think about exponent rules, if we have an exponent in the denominator and we want to move it to the numerator, we just make its exponent opposite. So if I want to move 1.3 squared up to the top, we need to make it 1.3 to the negative second, and then times 1.3 to the t. Okay, so now in our calculator, we can do 1.3 to the negative second power, and we get 0.5917. So I'm going to say f of x equals 0.59 times 1.3 to the t. And we look now at our growth factor, which is 1.3. And I said growth factor because it's more than 1, right? So we can say this is exponential growth, okay? All right, so that's a little bit about exponential growth and decay.